All right, looks like the numbers have settled now, so let's get started. Hello, everyone. Thanks very much for joining us today. Welcome to this COMET Plus webinar. It's great to see so many of you here. Just a quick note on logistics before we begin. The talk will be about 45 minutes, followed by around 10 minutes for Q&A. Please drop your questions into the Q&A box, and we'll pass them along to the speaker at the end. It's a real pleasure to welcome Dr. Yujie Zheng today. Yujie is currently an assistant professor in the Department of Sustainable Earth System Sciences at the University of Texas at Dallas. She previously held a postdoc position at the Seismological Laboratory at Caltech, and she earned her PhD in geophysics from Stanford University. Her research focuses on advancing InSAR techniques and applying them to study tectonic processes and near-surface Earth systems, including groundwater and soil moisture. Today, she'll be talking to us about modeling soil moisture using InSAR closure phase. So without further ado, I'll hand over to Yujie.
All right. Thank you very much for the introduction. So it's a real pleasure for me to be able to share my recent work with the COMET Plus community. And this is like actually very so because our university's mascot is also COMET, so this is very nice. And so, okay, as the title suggested, that today I'll be talking about modeling soil moisture from InSAR closure phase. So I have attempted to make the talk a bit concept focused so that so I'll try to build some physical intuition first of why closure phase is sensitive to soil moisture. And then I'll walk you through how we can model that. And at the end, I'll show you some results of soil moisture retrieval from InSAR closure phase. So let's begin with some bigger picture, broader context. Why does soil moisture matter? Well, soil moisture is a key state variable in the Earth system. It controls how water partitions between runoff, infiltration, and evapotranspiration. So as a result, it has direct influence on weather forecasting. It is a key variable or indicator for flood and drought, and it regulates agricultural productivities and hence is very important for food security. And because soil is the interface between the land and the atmosphere, it also regulates the coupling between water, energy, and the carbon cycle. So given the importance of soil moisture in the Earth system, the question is, what does an operational soil moisture product has to deliver? So for this figure, it shows the x-axis is the temporal resolution requirement, and the y-axis is the spatial resolution requirement for different applications. So different application domains will occupy different space in this chart. For example, climate models typically can tolerate coarse resolution spatially and relatively long temporal resolution as well. Numerical weather prediction is kind of similar, but requires higher higher temporal resolutions. On the other hand, applications for hydrology, disaster monitoring, agricultural, and forestry typically require much finer spatial resolutions. So if we overlay current satellite-based capabilities, we can see that the science community has made a lot of progress in terms of the passive microwave missions like SMAP and SMOS, and but they primarily provide soil moisture products at a coarse resolution on the order of tens of kilometers. On the other hand, active SAR missions like Sentinel-1 or NISAR can also produce much finer, they can also produce soil moisture products at much finer spatial resolutions. Sentinel-1 already produces operational SAR products at regional scales, and NISAR is going to provide a global level 3 soil moisture product at 200-meter resolution. It is important to note here that these SAR-based operational products are they use backscatter. So that means that they do not typically involve the phase information. So I want to talk a little bit about how SAR is sensitive to soil moisture. At microwave frequencies, radar interaction with the soil is governed primarily through the dielectric constant. So as the microwave reaches the surface, it can actually propagate, it can penetrate the soil to some depths. That is typically much smaller than its wavelengths, and as it propagates in the soil, it slows down and attenuates. So if soil moisture increases, what happens is that the effective dielectric constant will rise rapidly, which will make the propagation even slower and more rapid attenuation, which will cause more energy backscatter to the radar. So in practical terms, this means that if you have a wetter soil, you will see a brighter radar pixel. So this is the forward process. However, things become much more complicated when we try to invert the process. That means if we want to take a backscatter and try to invert for the soil moisture. So the core issue here is really the non-uniqueness of the inversion, because if effectively we have two unknowns, moisture and surface roughness, that both will impact the radar backscatter, and we only have one observation. In other words, different combinations of moisture level and surface roughness could potentially produce the same backscatter measurements. And in addition, vegetation and topography effects can introduce additional uncertainties. So essentially, while these backscatter-based algorithms are mature enough to deliver these operational SAR soil moisture products, the challenges are also well known. In fact, these complexities are also reflected in the mission level. For example, the NISAR level 3 soil moisture product will implement 3 different algorithms for soil moisture retrieval, and that alone tells us the challenge, because there just isn't a single universally robust way to invert backscatter for soil moisture. So that is the SAR. What about InSAR? Well, one interferometric observable that has been exploited for soil moisture monitoring is coherence. So this is an example done by Jordan et al. They modeled coherence in the Atacama Desert after a storm. And what they did is that they decoupled the coherence change into 2 parts. On the left is showing the transient InSAR coherence change associated with the rainfall and the moisture change. And on the right is the permanent InSAR coherence change that is associated with lasting modifications for the scattering surface. So the transient component can be interpreted and modeled for soil moisture. And so this approach obviously requires decoupling of multiple processes that can lead to decorrelation. And as you can see here in this example, that in the hyper-arid environment, this decoupling can be done quite beautifully, and that works very well. However, you can imagine that this decoupling process can be much more complicated for more complex environments, and when you have to separate effects like vegetation growth, roughness changes, etc., that could be significantly more challenging. Another issue for using InSAR coherence for soil moisture is the sign ambiguity, because either increase in soil moisture or decrease in soil moisture will result in the same InSAR coherence. So that's also a fundamental non-uniqueness. So essentially, coherence is, while it is clearly sensitive to soil moisture, using coherence alone for soil moisture inversion is also challenging. So the next on the list is obviously the InSAR phase measurement. And we know that InSAR phase can be sensitive to soil moisture, and this is an example of a 6-day raft interferogram over the Central Valley, California, where there are a lot of agricultural fields. And as you can see, there are clear field scale variations in phase that align with the agricultural parcels. So these phase variations they could reflect differences in the soil moisture. They could reflect differences in the vegetation water content. They could also reflect differences in the crop growth and etc. So what we can say here is that InSAR phase is sensitive to soil moisture in the scattering phase component. But the challenge is that these phase components, more often than not, are superimposed by other much larger path delay phase effects. So here I want to distinguish what I call the scattering phase from the deterministic phase components. This is a simplified picture of microwave interacting with soil. As you can see, the incident wave penetrates the surface and interacts with multiple scatterers at different depths. And each of these scatterers will contribute a complex return with some amplitude and its own phase delay. And we can divide the phase delay into two parts. One is related to the propagation within the soil. So the D here represents depths to each of these scatterers. And the wave number here is a function of the soil moisture. So this is the scattering phase that I'm talking about because it reflects the propagation of the microwave within the soil. And on the other hand, we have the deterministic phase, and it is related to the common distance between the radar and the ground. So in conventional InSAR analysis, the scattering phase is often ignored because we usually assume that if a pixel remains coherent, that means all these little scatterers are not moving too much relative to each other. And if they do, we have a decorrelated pixel. However, now we know that even if these scatterers are not physically moving, just changes in the soil moisture will lead to changes in the effective wave number, which can lead to a systematic non-zero change in the scattering phase. So the problem for soil moisture retrieval is how do we separate the scattering phase from the deterministic phase components? So this is where closure phase comes in. I think some of you are familiar with closure phase. So it is constructed from 3 or more interferograms forming a closed loop in time. And the phase components that are deterministic and additive in time, such as deformation, atmospheric noise, they will cancel when summed around the loop. And what remains is the non-closure component, which reflects the nonlinear scattering phase component. So I'll explain why it is nonlinear. Well, the nonlinearity really arises because of the distribution of scatterers within a three-dimensional space. And we can sort of simplify that as multiple scattering layers with depths. So the plot on the left shows a simple case with two layers, a black layer and a blue layer. So when soil moisture changes, the dielectric constant changes, and that means two things. First is because of the dielectric constant change, we have a change in the effective wavelengths. And therefore, that means the phase delay accumulated between the two layers will change. And so that means even if the layers are not moving physically in time, moisture variation will make them appear closer or further away from each other in radar's view. A second thing that happens is moisture change also modulates attenuation so that the relative brightness of each of these layers also change. So what that does, it changes the relative contribution from each of these layers. And because we know that what the radar measurements is a coherent sum of the coherent sum from contributions of all the scattering layers, these phase shift changes and amplitude reweighting will fundamentally change the interference patterns between these contributions. And these are the sources of the nonlinearity. So closure phase, therefore, in a sense, shines the spotlight exclusively on the scattering phase, which is nice because if you have worked with closure phase or you have worked with InSAR data, you know that it's always very nice to work with observables that are not contaminated by atmospheric noise. However, it is still by no means a straightforward observable to work with. And this is because the closure phase is not a direct measurement of the scattering phase. In fact, what it really measures is the departure from linearity. And even if we assume uniform moisture with depths and uniform scattering density so that we have a relatively simple looking description of the scattering phase as shown by the equation here, what closure phase measures is the argument of the triple product of these nonlinear functions of wave numbers, which we then hope to translate to soil moisture. So this is a very difficult inversion problem to solve. It's similar to the other InSAR observables we talked before, and it's also very computationally expensive. There are a lot of work has been done in that front, mostly trying to work out clever ways to make the inversion easier and faster. But my motivation is that what if we can find an observable that is simpler to work with? And that is where closure phase bias comes in. So closure phase bias was initially reported as what we call the fading signal that exists predominantly in the small baseline interferograms. So in this example, by Ansari et al., it shows that the same InSAR dataset is processed multiple times, but each time with different maximum temporal baseline. And the result shows that the estimated deformation will systematically change as we shorten the temporal baselines. And here over Sicily, Italy, you'll see that when only short temporal baseline interferograms are used, the results show apparent subsidence. But as we introduce more and more longer temporal baseline interferograms into the network, that apparent subsidence diminishes. So when we repeat the same experiment, but over the Mojave Desert in California, we observed a very similar baseline dependent behavior, but this time we actually saw apparent uplift. So we now understand that these so-called fading signals is not a processing artifact exclusive to the short baseline approach. It really reflects physically meaningful moisture-induced changes in the soil. In fact, I want to briefly sort of take some time to emphasize that these physical signatures does not vanish when you use full network inversions. For example, if we look at JPL's NASA JPL's Opera displacement product, which is generated using a full network, full resolution inversion algorithms and are very nicely available through the displacement portal in ASF Vertex. So this is a screenshot over the Los Angeles area. And this is the displacement velocity produced by the Opera displacement products. And you'll notice that this large coherent region of light blue, so that actually corresponds to a long-term subsidence associated with oil and gas production in the Beverly Hills region, and that is on the order about 1 centimeter per year. But there are a lot of other things going on, and I circled a few here. So these smaller localized patches of darker blue areas are actually golf courses. They align very well with the footprint of the golf courses. And it is very unlikely that each of these golf courses are undergoing very localized subsidence at rates significantly larger than 1 centimeter per year. A more plausible explanation is that these signals reflect moisture-driven phase effects that in fact persisted for full network, full resolution displacement products. All right, so that's a quick detour. So now back on track. So the reason we now call fading signal also the closure phase bias is because we figured out that we can actually use closure phase to predict the fading signals. So the idea is kind of simple. Because we know that closure phase measures the departure from linearity, so sequential closure phase effectively measures the nonlinear phase residual between consecutive acquisitions. And if we cumulatively summing this nonlinear phase residual over time, we can reconstruct a bias time series. And we can use that to predict the various bias effects in different networks. And finally, we can remove the predicted bias from the displacement solutions. So what's more interesting is when we looked into the reconstructed bias time series at individual locations. For example, this is a reconstructed closure phase bias on the edge of the Bristol Dry Lake in the Mojave Desert. And you can see that the closure phase bias time series here exhibits a sequence of step-like changes. And if we look at the precipitation history in this region, you'll see that these step change increases align closely with the precipitation events. So this is very interesting because this suggests that closure phase bias time series could potentially be used to learn about soil moisture, and it's much visual and simpler and straightforward than working with closure phase itself. And now, since we know that closure phase bias is not simply a noise that we want to remove, but can also be a signal that we can use, I'm going to go ahead and remove the term bias and from now on call it closure phase time series instead. So what makes closure phase time series interesting for soil moisture retrieval is because we observe this simple step-like response to rainfall events, which suggests that it is sensitive to moisture anomalies. So here it is important to note that the sensitivity is to the anomalies rather than the absolute moisture values, because only changes in the moisture level will cause the observed step-like changes in the closure phase time series. Additionally, what's attractive about using closure phase time series is that it can be calculated in different ways. So it can be derived from time series products. It can also be derived using sequential closure phase. And we know that there are already many time series products are available at regional and national scale. So that makes closure phase time series also scalable computation-wise. So what's next, or the next step, is really trying to find the mathematical relationship between closure phase time series and soil moisture anomalies for, and we can do this the hard way, which would be try to derive it analytically. That becomes intractable very fast. We can also do it using numerical simulation, which is my preferred method, because numerical simulation often not only is simulation more practical, but oftentimes it's very informative as well. So next I'll introduce a discrete multi-layer scattering model. So what we do is that we approximate the soil as a finite number of discrete scattering layers at different depths. Each of these layers will contribute a complex return with some amplitudes and some phase. And soil moisture enters the model through the dielectric constant, which determines the effective wave number, so that the total radar return is then the coherent sum of all these contributions. And the advantage of using a multi-layer model is that now we're not restricted to uniform moisture with depths. We can allow soil moisture to vary as a function of depths. Therefore, you see all these little subscripts in here. So that's each of these layers can have its own wave number. We can also allow for the brightness of each layer to vary. So that's the subscript in here for the amplitudes. So this allows some flexible construction of the model. For example, we can even include vegetation layers above the soil surface if we wish. And so what this model does so far is that it simulates one single look radar pixel. And if we simulate multiple times, we can actually create a single look radar image with n pixels, multiple pixels. So with that, we construct a forward simulation pipeline, which allows us to observe the impacts of various physical inputs, such as soil moisture time series, radar frequency, and soil texture on the output, which would be the closure phase time series. So I'll walk you through a simple baseline scenario to build some intuition. So for the baseline simulation, we'll assume an arid environment, and we'll assume uniform moisture with depths. So that means there is no moisture variation with depths, and we'll assume a sandy soil texture. So we'll first convert these inputs into dielectric constant using a standard empirical model, which can then be converted to the effective wave numbers for each of these layers. Because if we're assuming uniform moisture with depths, in this case, the wave numbers are actually the same across all the layers for any given time. We then we can do this for multiple times to form a multi-look window of 400 pixels. We then multi-look the measurements and proceed to do time series analysis with different network. And then we compare the difference to generate the closure phase time series. So here is the input for the baseline simulation for the arid case. And for arid environments, we typically have a low baseline soil moisture with positive soil moisture anomalies induced by precipitation. So here we assume a period of time with 3 rain events. Each rain event would cause a fast wetting of the soil by the rain, and then a slow drying period of the soil. And just we also make the magnitudes and duration of these anomalies different to see the correlation. And the patterns of bias we observe in the simulation is shown here, and it actually really closely mimics the real-world observations we had. Firstly, you can see that the closure phase time series is cumulative for each of the rain event. And furthermore, we find that these apparent uplifts or step changes in the closure phase time series corresponds to the drying of the post-rainfall soil drying period. And last but not least, the size or the magnitude of the step change and the duration of the step change also closely follows the magnitude and durations of the soil moisture anomalies themselves. So now let's consider the first variation to the baseline simulation. So we'll still consider a uniform soil moisture with depths, but now in a wet environment. So the input soil moisture time series now has a high baseline soil moisture value. And instead of positive soil moisture anomalies, we have negative soil moisture anomalies. So this is not something that I made up. It's really inspired by in situ measurements. So this is an example of in situ soil moisture measurements in the wet environment. And so this is for 1 year. And you can see one negative soil moisture anomaly and lasts about 4 months between July and November. And this is typically caused by evapotranspiration exceeding precipitation. and they typically last much longer than soil moisture anomaly for that reason. And you can see that it has the signature of fast drying and slow wetting signature. Okay, so for the simulation, we'll keep everything else the same with the baseline simulation. And we find that the predicted closure phase time series have very similar patterns with the previous case, except that there is a sign reversal. So far, we have assumed uniform moisture anomaly with depths. So now let's relax that assumption. So in this next experiment, we allow the moisture anomaly magnitude to decrease with depths. So here, the y-axis is depth, the x-axis is time. So we see the same 3 positive soil moisture anomalies, but the near surface layers have larger anomalies than the deeper layers. So this represents a more realistic infiltration scenario where near surface layers will usually experience stronger moisture changes than the deeper layers. And here are the results. So comparing to the uniform case, we find that the cumulative closure phase is reduced, which is very much expected because we know that the closure phase time series is the integrated response from all the layers at depths, and now we have reduced the contributions from the deeper layers. Therefore, we see a reduced overall response as well. Just to make things a little bit more complicated, now we're adding another variable, which is the radar frequency. So we're keeping it in the arid case with varying soil moisture with depths, and now we're testing the response for different radar frequencies. And the motivation of this experiment is to test the hypothesis that whether larger wavelength radar generate larger closure phase just because of their greater penetration depths. We find that this is actually not the case. So here are the results. So this is the predicted closure phase time series for X band, C band a lot larger, S band slightly larger than C band. But when we come to L band, it actually is smaller than C band. So that is somewhat surprising initially. So let's think about what actually happened as we go deeper into the soil column. So as depth increases, 3 important processes occur simultaneously. First of all, we have increasing geometrical phase accumulation, just because as we go deeper, the propagation path becomes longer. Secondly, as the wave propagates downwards and back, attenuation will strongly impact the effective contribution from the deeper layers. So in a sense, the deeper layers have 2 competing mechanisms. On the one hand, it has more geometric phase accumulation because of their depths, but on the other hand, because of attenuation, their contribution to the total weighted phase is smaller. And for the simulation we did, we also have a third factor, which is decreasing soil moisture variation with depths. And with simulation, we can actually visualize the contribution from each depth layer. So this is the contribution from different depths for C band. And as you can see, the contribution is really dominated in the top few centimeters near the surface. But when we repeat the experiment for L band, we see something very different. The depths of maximum sensitivity shifts downwards, and the region that contributes most to L band almost does not overlap with the C band sensitivity region. So in other words, C band and L band are almost not measuring the same portion of the soil column. They're really sampling physically distinct depth ranges. And in this case, since we have the soil moisture variation decrease with depths, L band is integrating phase contributions from layers where the anomaly amplitude is smaller, while C band is concentrated in the shallow layers where the soil moisture variation is strongest. So as a result, we show that L band can accumulate less closure phase than C band, despite its deeper penetration. Okay, so the last simulation, so in all previous cases, we have tested asymmetric moisture anomalies, either rapid wetting followed by slow drying or vice versa. Now we test a purely symmetric moisture variation. And in this experiment, so you see that soil moisture varies periodically and symmetrically in time. And the predicted closure phase time series is also periodic. So there is no cumulative bias. So this confirms that cumulative closure phase really arises from temporal asymmetry in moisture evolution. Okay, so a quick little summary for what we have learned so far from the forward simulation. So first of all, we find that closure phase is sensitive to soil moisture anomalies, not absolute moisture. And the sign of the closure phase step changes reflects the direction of the anomaly, so that the positive soil moisture anomaly leads to positive step changes in the closure phase and vice versa. And also very importantly, we find that the magnitude and duration of the step change in the closure phase scales with the magnitude and duration of the soil moisture anomaly. We also find that temporal asymmetry is a requirement for having cumulative closure phase. And if you have symmetric oscillations, we don't really observe cumulative results. And very importantly, we find that radar frequency has different depth sensitivities. And when we use longer wavelengths radar to get the sensitivity to soil moisture, it is really important to take into account the depth variation of soil moisture. All right, so with all these insights from the forward models, now I'll attempt to find a mathematical relationship between soil moisture anomaly and closure phase time series. And my hypothesis is that the closure phase time series behaves like an integrator of moisture anomalies. Mathematically, that means we can integrate moisture anomaly with time, and the corresponding closure phase time series is a scaled version of that. So this hypothesis is really built on the observed relationship between the soil moisture anomaly and the closure phase time series, especially for the correlation between the duration of the anomaly and the duration of the step change. So if you imagine a soil moisture anomaly with zero duration or very finite, very small duration, the closure phase time series will jump instantly like a step. So in a sense, this says that if there is an impulse response to the system, the impulse response is a step function. And if you have an impulse response of a step function, the system acts like an integrator. Here, the extra scaling factor is because the step change might not necessarily be unit height. So to test this, we start with a soil moisture anomaly that decays exponentially over time. For an integrator, the predicted closure phase time series will be a saturating exponential. So we then fit this functional form to the closure phase time series produced by simulation, and we find that this matches almost perfectly. So what this does is that it validates our hypothesis, but since we only tested for soil moisture anomalies that conform to exponential decay, we are only validating our hypothesis for this subsection of soil moisture anomaly. But this actually exponential soil moisture anomalies that has exponential decay is actually the most commonly used models for soil moisture. So with this framework, we can easily reverse the process, and we can take a closure phase time series, differentiate it, and retrieve soil moisture variations. Here we choose to normalize rather than recover the exact coefficient, because that part is the nonlinear part of the system, and it's very tricky to do. So by normalization, what we get is what I call the InSAR soil moisture index. And it's important to emphasize again that this is not a direct measurement of volumetric soil moisture. it is rather a scaled, unitless observable that captures soil moisture variation dynamics. So we first apply our algorithm to Sentinel-1 observations over the Mojave Desert in California. So here, soil moisture anomalies are primarily driven by rainfall and follows closely to the pattern of exponential decay. So that's why our hypothesis should really work in this area. And in this plot, the gray dots are the in-situ soil moisture measurements. The crosses are SAR acquisition dates. And you can see a number of clear positive soil moisture anomalies that corresponds to precipitation events. And using our algorithm, we recovered the InSAR soil moisture index, and it actually did a pretty decent job of recovering most of the significant soil moisture anomalies. The main limitation here is really the temporal resolution of Sentinel-1, because it's every 6 or 12 days. If you have soil moisture anomalies that are closely spaced together, it is harder to differentiate them. But overall, the agreement is excellent. So that's the easier case where for the Mojave Desert, now let's move on to California Central Valley, where soil moisture dynamics are much more complicated, and we expect because not only rainfall modulates the soil moisture, but we also have irrigation, crop growth, groundwater, etc. So this would be a good environment to test the applicability of our hypothesis beyond exponential drying assumptions and beyond the arid environments. And another reason that we chose to test in Central Valley is because the data quality is actually still great, and we have good correlation for short temporal baseline pairs. And this is what I'm showing here is the average closure phase bias over the Central Valley. And you can see this clear apparent subsidence nicely overlaying the agricultural fields. And in fact, if we zoom in, you can even start to see correlation between the closure phase bias and the different crop fields. So here the main crop fields are rice, walnuts, and clover and wildflowers. Okay, so next I'll play you a video of the derived InSAR soil moisture index. And if the color is blue, that means for that point, soil moisture is wetter than average. And if it's red, that means it's drier than average. So for a video, it has a lot of information. So we're gonna look at a still image in a second, but I just wanna give you some sense of the general quality of the measurements. And you can also pay attention to some of the fields that are labeled here, okay? So here is the video. You see seasonal variations. And what surprised me initially was even for the forest areas that except in the winter that you have decorrelation, for a lot of time, we actually have coherent observations. All right. So now I'm showing you a seasonal change in the InSAR soil moisture index. So this is the difference between the derived InSAR soil moisture index observed between a summer date and a winter date. And you can see the colors here, blue means that it's increasing of soil moisture, and red will mean a decreased soil moisture. So you can see the agricultural fields show generally blue colors, which is expected. And we can compare that with the SMAP Sentinel-1 level 2 products. And we see general consistencies between these, the InSAR soil moisture index and the SMAP Sentinel-1 products. But obviously, the InSAR products will have much higher spatial resolutions. We can also look at individual fields. So here, the yellow dots are SMAP Sentinel-1 products. The purple curves, the purple diamonds, and the black line are InSAR soil moisture index. And we can see a great agreement. That's the walnut fields, and this is the wildflower fields. Again, we're capturing the seasonal variations. And for the rise field, it's another story. So in this one, the agreement is not that great, but rise fields are difficult to measure for SAR or InSAR. So we'll need more validation to test this. I just want to quickly mention that if we compare the soil moisture measurements of the walnut fields and the clover and wildflower fields, and this is showing the SMAP Sentinel-1 products, you'll see that the measurements are actually very similar for these two different agricultural parcels because one is likely irrigated and the other is not. But for InSAR soil moisture index, you see quite different magnitudes of soil moisture variations. Especially, it's suggesting that the clover and wildflower fields has larger anomalies, which I think is expected because clover and wildflowers, these are fields are likely not irrigated, so that it's likely to experience more larger negative soil moisture anomaly in the summer. All right, so that's all I had, and just a quick summary. So what we have learned. So we have seen that closure phase is not just a mathematical artifact. It really emerges naturally from moisture-driven changes in both phase accumulation and amplitude reweighting with a multi-layer scattering systems. And through simulation, we can predict how different inputs can impact the closure phase time series accumulation. The key thing, the highlights here is the depth variation of moisture and the radar frequency has different sensitivity of depths. And based on these insights, we have a hypothesis that the system behaves like an integrator and differentiator. And we validated this hypothesis for soil moisture anomalies that exhibit exponentially decaying patterns. And finally, we moved on to the real data and showed that the hypothesis can likely generate to more diverse environments, as shown by the case study in the Central Valley. And in the end, in the future, is probably the best, the path forward is probably to try to combine all these observables that I mentioned today for soil moisture to have a more robust retrieval. And that is all I have. Thank you.
Thanks very much, Yujie, for a great talk. Now, let's open it up for questions. We've got a couple of questions from the audience. Do you consider the shrink swell of clay?
So the shrink swell of clay is more like a physical movement. So that's what I sort of define as the deterministic phase components that will be canceled in the when you form closure phase. So it's probably not in the closure phase signature, though it is correlated with moisture change.
Can InSAR detect the smallest change in the soil moisture, or is there any threshold soil moisture change value which can be noticed by the InSAR closure phase?
That is a great question. So the examples I have shown are the moisture anomaly magnitudes are like the absolute moisture variations are about like 20-30%. Well, I guess the short answer is I don't know what's the threshold. It will require more work. And in theory, the long answer is in theory, it should be the same with the detection of the displacement threshold. So it really depends on the noise level. So one thing with closure phase that's similar to displacement retrieval is that we can only work for data that has good coherence, right? So I suspect it's gonna depend a lot on the quality of the measurements, and obviously more experiments and validation needs to be done to really get that threshold value.
Okay, thanks. One more question. Please list the tools available to quantify soil moisture from InSAR closure phase.
So to quantify soil moisture from InSAR closure phase, there has been a couple of studies that I have listed as a reference in the talk. And if you reach out to me by email, I can send you some references. But basically, there are groups based on closure phase itself. And that's largely done by Francesco Dizon. And they have algorithms available, but I'm not sure if there are computational tools available. But there are some work that has, I think, open source GitHub repo that you can try with closure phase. And for my own work, this one, because it's still we just have this hypothesis and test it, and we're still working on getting the repo public.
And what do you think, does this closure phase works better when there is anomaly in soil moisture?
So the question is about what do you think, does this closure phase works better than there's anomaly in soil moisture? I will interpret that as asking about why closure phase works better for soil moisture anomaly detection. Well, I'm not sure what the question means actually. But closure phase, because it's not a direct measurement of the scattering phase, it's measuring the departure from linearity. So if you have zero change in the moisture, it wouldn't generate any closure phase, right? So it's only sensitive to soil moisture variations, and it's only sensitive to asymmetric soil moisture variations. So that's the limitation here.
Just as a point, we do have one hand raised by Dr. Hamdi Imad. Sorry, we can't take any live questions, but if you can pop your question in the Q&A section, then we can get that answered. Just before, I just want to jump in there.
Another question. Could you please explain again how the level drop in the spike change is resolved from the differentiation, please?
The level drop in the spike change. I'm sorry, I'm again not fully understanding the question. I think it's about the retrieval algorithm. So the level, okay, so it's probably like, how do we actually get the magnitudes of the anomaly, right? So actually, when we differentiate the closure phase time series, we normalize it to be between 0 and 1. Is because the level, like the magnitudes of anomaly, is very hard to retrieve exactly because the system is very nonlinear. What we are doing effectively is to find a linear approximation of the system. But the sacrifice of that, or the trade-off of that, is that we sort of let go of the part where we try to recover the exact magnitudes. But spatially, right, when we normalize it over a large area, it will normalize to the largest anomaly, so that you see spatial variations, because some areas experiencing larger anomalies, some areas experiencing smaller anomalies. Not sure if I answered that question, but I'm happy to discuss later by emails if you wish.
Thank you. For L-band NISAR with 12-day revisit, what is the minimum number of acquisitions needed for reliable closure phase soil moisture index computation? Is 3 to 5 pairs sufficient, or do you need a full temporal stack? And can the closure phase SM index can be used as a physics-based training target for deep learning models instead of self-supervised reconstruction, essentially using the SM anomaly map as ground truth for a CNN transformer architecture?
These are great questions that I'm actually thinking about myself. So for the first question about L-band InSAR, how many acquisitions is needed to get this computation? So technically, you can do the mathematical operation for any number of acquisitions, but realistically, we want to have enough temporal sampling over one anomaly at least. So it also depends on the area. Like for example, for the arid cases, the temporal sampling of existing satellite emissions are pretty great already, so that we can resolve individual anomalies. Mostly. For agricultural fields, you see much more complicated scenarios. So right now, what I'm showing is more sort of the longer term variations. So you don't really see the fine temporal resolution. The shorter scale variations in soil moisture. So one thing I'm actually interested to see is whether if we have experiments that can be done on more frequent samplings of agricultural fields, do we actually also resolve the shorter scale temporal variations? Yeah, and yeah, so if it's 12-day revisit periods, 3 to 5 pairs are probably too few in my opinion. And okay, so the second question about using physics-based machine learning, that is exactly what I'm trying to pursue right now. And I think the inversion, like machine learning is more and more used for inversion processes, and this is very good example of where you have a very complicated system mathematically between soil moisture anomaly and closure phase time series, but we also observe this very simple relationship that we can actually approximate with a relatively simple looking mathematical equation. And that's something I think machine learning could potentially do much better than what I just showed here.
Okay, thank you. I think we are about out of time, so I think we'll have to stop there. Sorry, couldn't get to all the questions. If you reach out to Yujie, I'm sure she'll be happy to answer your questions. And yeah, thanks again to Yujie, and thanks
you.
everyone for joining. The recording will be available on YouTube, and have a great rest of your day or evening, wherever you're joining from. And we hope to see you again at our next webinar in March. Thanks, everyone. Thanks, Yujie.
Thank you. Bye.